Hi. So I'm Dominique from Switzerland, and I run a small consulting company. And in a previous live, I was doing smart card security for pay television. Okay. So today I'm going to talk about WPS. If you don't know what it is, I will explain. Thank you, sir. So WPS stands for Wi-Fi Protected Setup or Wi-Fi Simple Configuration. And it's a way to easily set up your Wi-Fi network at home if you don't want to enter this. Sir? No kittens today.
No kittens.
No, I'm sorry.
Next year.
Next year. No kittens. Really sorry about that. So where was I? Yeah, it allows you to join a Wi-Fi network without having to type these very complicated and annoying secure passphrases, you know. And it offers several ways to do that. And as I will show you, it's a very broken protocol. And actually, you can see that by yourself by purchasing the specification for $100. And if you don't really want to spend the money and you have some good Google foo, you can find an older version on the net somewhere. So, how does it work? What it is exactly? There are several ways to configure WPS. One way you might have seen on your Wi-Fi router is to press on a button. That's called the push button method. But here I'm going to talk about the pin method. So if you have ever looked at your Wi-Fi router, you might have seen that on the bottom it has its MAC ID, and it also has an 8-character pin code, 8-digit pin code. And if you want to play a little game, there is something hidden in the 2 barcodes. That's Angel Albertini who did this little picture. So you have this 8-digit pin code under your device, and it's already not very big. And when you connect to your Wi-Fi access point, if you have this protocol enabled, you will see that instead of asking you for the WPA passphrase, it will ask you to just enter the 8-digit pin instead. And so one thing that people always tell me is that, yeah, but it's not such a problem because you have to enter the pin, but you also have to press the button, the WPS button on the router. But that's wrong. That's 2 different protocols. There is one protocol that uses only the button, and there is another protocol that uses the pin code. So it's an or, it's not an and. So we'll go a bit more into some technical stuff, some definitions. According to the specification, an enrollee is a device who wants to join a Wi-Fi network. A registrar is an entity who is allowed to give the credentials to the network. And an external registrar means it's not the access point. That means it can be any machine, actually. It can be another device which is already on the network, like a laptop. It can be an LDAP server. It can be absolutely everything. And an access point, everybody knows what it is. And an important point, a headless device is a device that doesn't have a screen. Like an access point, usually they don't have a screen. So more graphically, let's say you have a Wi-Fi network. And you would say, from the definitions I gave before, the logical thing is that the register is the access point, and you have 2 devices, enrollees, who want to get on this Wi-Fi network. But as I said, the register could also be a device that is already on the network. And there the communication goes over UPnP. But what actually happens most of the time is that the access point is the enrollee, and the device that want to join the network are the registrars. If it makes no sense to you, yeah, it doesn't make sense, but it's that way because otherwise the protocol will be even less secure. So That's exactly just what I said before. A registrar doesn't actually need to already be in the network. Yeah, or you can also have many registers on a network. So that's just what I just said. So let's see this PIN protocol, how it works, actually. So, as I said, the access point is the enrollee, and the registrar is actually the laptop who wants to join the network. So, the first thing to know is that you have the PIN on the sticker. It's actually not 8 digits, but most of the times it's 7 digits, because the 8th digit is a checksum. There's actually two types of PIN. There's what is called the default PIN, which is written on the sticker, which is 7 digits plus checksum. And you can also have a user-selected PIN, which you enter on the web interface of your router, and then it doesn't have a checksum. It's really 8 numbers, 8 digits. But to make matter worse, it's not actually 7 or 8 digits. It's 2 times 4 digits. It's separated in half. It's actually 2 4-digit pins to make matter even better. So you might think that the Wi-Fi Alliance doesn't know about these problems, but if you look at the specification, they actually know. Like, they know that a pin should only be used one time. That is, if you do a try for a pin and it doesn't work, like the user entered the wrong pin, you are supposed to issue a fresh pin. But that only works if you have a screen on the device. If it's a sticker, you cannot change the pin on the sticker. So on headless devices, you are actually always using the same pin. And as you see, the specification says that you should never reuse a pin. And it also says that, well, if you have a sticker pin, it only has 23 bits of entropy, and it's susceptible to active attack. So they actually knew that already when they released it. So how does the protocol work? You start with the standard Wi-Fi stuff, so I won't go into that. Beacon, probe request, authentication, association. That's boring standard Wi-Fi stuff. And then you have all these messages in the protocol. It all goes through EAP, which is, I think, extended authentication policy or something. And so, one thing we have to know is that the protocol uses something called pre-commitment. That is, both sides have to prove they know the password, the PIN. Because if it was just the user giving the PIN to the access point, and the access point is an evil access point, like a fake access point, then he will know the PIN. So they needed a way in the protocol to make sure that both sides authenticate each other. It's a bit like if you need to meet someone you don't know, and you both have half of a banknote. When you meet together, you check that both halves match. So that's really the person you need to meet. OK, so how does that work in practice? The first thing is the access point sends random nonce to the laptop. And it's public key. And it's not very important at this point why, but usually it's a good idea to have some random number in cryptographic transactions so that messages cannot be reused by an attacker in later protocol runs. Then, well, the second message is not very important either, but that's the laptop who also gives a nonce, a random number, to the access point. And they use that to generate some keys, but I won't go into details here. And then what is interesting is that it gets interesting now. The access point sends 2 pieces of data, encrypted pieces of data, to the laptop. These pieces are encrypted with a random key. So basically, if you want, it's the 2 halves of the pins encrypted with 2 different random keys. So if you want, it's a bit like if the access point was giving you 2 boxes with combination locks, where it has hidden inside both halves of the pins with a very long combination on the safe, so you cannot open it. So in advance, you say, hey, I'm going to show you that I know the pin. I wrote it on 2 pieces of paper, put them in 2 safe boxes, put a very long combination, and I'm giving that to you. You cannot open it, but keep that for now. So then the laptop does the same. It says, hey, I also write the 2 halves of the pin code to prove later that I know them, put them in little safe boxes with very long combination, and send it to the access point. So where was I? And yeah, it also directly sends the combination lock, the combination of the first safe, if you want. So what does the access point do then? It uses the combination to open the little safes. That is, it will verify that if it hashes the PS key 1 is the first half of the pin with the random number given by the laptop and the public keys, if it hashes to that, all this stuff, it verifies that it matches the number that it matches this number. So if the laptop actually knows the first half of the pin code, the numbers will match. If they don't, it means that the laptop doesn't know the pin code. So if it does, then the access point is happy, and it will send the first key to the laptop. So it says, OK, you showed me you know half of the pin code, so now I show you I know half of the pin code. And so now the laptop can verify with the same method, with the same hashing, that the access point actually knows the first half of the pin code. So now that the laptop is happy that the access point knows the first half of the pin code, so I do the same for the second half. So sorry. And once they both have verified that they each know both half of the pin codes, the access point will send the WA passphrase of the network to the laptop. So one thing that also is amazing, it doesn't give the key of the network. It gives the passphrase, the actual passphrase. So it means that it's always stored in clear in the router. That's already pretty bad. So you can see that it works pretty well if you use a pin only once, because you have these 2 parts. If it doesn't work at the first half, they just say, no, you're not the right guy, let's stop. And you're supposed to start with a fresh pin, which is not possible with the sticker. So what happens is that in 2000, yeah, that's what I just said. In 2000, that was, I don't remember which year, if it was 2008, someone already at ACLU said, hey, you know, if you don't use freshly generated pin, you can probably brute force the pins. But no attack was published at the time. And in 2011, Stefan Wieberg published an attack. He published a tool that can actually brute force these WPS protected Wi-Fi. Thing is, since the pin is separated in 2 halves, you can just easily brute force each half, and there is no protection on the Wi-Fi routers. So you just ask the router, hey, I think the first half of the pin is 1. No, sorry, start again. Hey, I think the first half of the pin is 2. No, sorry. And you can do that as much as you want. And since it's only 4 digits, you have 10,000 tries for the first half, and if it's a sticker pin and it's 3 digits plus a checksum, you only have 1,000 possibilities for the second half. So you can do that in 4 hours. Depends on the access point, but in a few hours, like usually 4 hours, you could really brute force any WPS pin. So if you want to do that, there are tools available called Reaver or Bully you can download. So that was really bad. Like most routers at the time had this protocol, and you will get into any Wi-Fi in 4 hours. And still kind of the case today, unfortunately. So what did the Wi-Fi Alliance do at this point? They changed the specification, and they said that in case of a static pin, the devices must take strong mitigation. So what they usually do is that nowadays, after like a few tries, like after 5 tries, you will have to wait 5 minutes before you can try again. But still, it slows down the attack sometimes from 4 hours to 1 day or 1 week. But depending on what you're attacking, if you're attacking a bank or something, you probably don't mind having a device waiting for 1 week to just brute force. Some manufacturers have been a bit smarter. They actually lock until the next reboot. You do 5 tries, and then it's locked until the next reboot. You might think that's secure, because 5 try and wait until the guys reboot. But that's showing in Bully, for example, say WPS lockout sleeping for 43 seconds after 3 pins tries. So you might think it's secure, but actually, one thing that is very important for these Wi-Fi routers is that they always work. Is that you don't come home and you're like, oh my God, it's not working again and stuff. So they usually have watchdogs. So they have software that's like, if they see something strange, they just say, hey, let's reboot. So let's go into a clean state. It looks like I'm going slow or whatever. I'm out of memory or something. Just reboot. So people have released scripts that will just flood the access point, and it will reboot. So, thank you, sir. So, here it's very easy to just flood the device, wait for it to reboot, and you can have 3 or 5 more tries, and so. So again, it's totally doable. But then I was looking at that this summer, and I say, hey, there's something else that is strange. There is this nonce that is random, generated by the unruly, that is not really useful unless you want to prevent protocol reruns. And also, these ES1 and ES2 are also random. And they are 128 bits. But that's kind of the combinations for the safes that the access point gives you at the beginning. When like, if you find them, actually, if you notice combinations, the access point has actually given you the pin code. But see, if you can find these 2 values, then we just brute force PSK1 and PSK2, which is like 11,000 tries on the PC. It's instant. But if you're an academic, you are going to tell me, it's 128 bits. You cannot brute force that. And if, like me, you have worked on smart cards and embedded systems for a long time, you ask yourself, how the hell do they generate these random numbers? And usually they use pseudo-number generators, which have, I have a cat, actually. But I don't know if it's a cat. It's a devil or something from Dilbert. So they use very insecure random generators that have like 32 bits of entropy. So that means that the random number, instead of being 128 bits of entropy, only has 32 bits of entropy. So the question is, can we recover the state of the random generator? So let's see how it's done in Broadcom. That's a brand of chips for routers. Well, that's code that is supposed to be secret, but they put it on GitHub. And here is the random number generator. Yeah, to generate a random, they basically use the rand function from C, which, as you know, is not a secure random. And the actual function is that it's a simple congruential generator. So I'll go pretty fast. So yes, 32-bit state, no entropy, and what you see is that the routers first generate this 120 bits, 8 bits nonce, and then it will generate the first random key, and then the second random key. So what you can do is that you get the nonce, and from the nonce, you recover the state of the random generator. You just basically try and generating numbers, starting with different seeds, until you find the same nonce. And once you have that, you have recovered the state of the PRNG. And it takes 32 minus 7, it was 25 bits of entropy or something, so it's instant. And so once you have both ES1 and ES2, you can just recover the pins. So in one try, in one single try, you recover the pin. So yeah, let's go a bit faster. Then I tried to see, I checked on another brand, Ralink. So these guys, they didn't use they didn't use a congruential generator, but they use linear feedback shift registers. As you see, basically, you have the state here, 32 bits, and each time you get the bit of output, you just shift to the right, you XOR some of the value you have in the state together, and you put it back at the beginning. So here, it's even easier to get the state, because from 32 bits of output, you basically get 32 bits of output, so that's 32 bits of the nonce. From here, you basically have the state 32 bits earlier. Don't even need to brute force anything. You just get the state from the nonce. And then I tried for several days to recover the nonce. I could recover the state and the nonce very easily, like 32 bits, and I got the rest. It works perfectly. But no way to get this ES1 and ES2 from that. And I looked in the code. I could really not find it, how they did it. Like, those guys are smart. I really cannot find how they generate ES1 and ES2. And at the end, I found out that they never generate them. They're always 0. So if you have a Ralink-based access point, you can always decrypt. Basically, the safe combinations are always 0, so you can always recover the pin very easily. Okay, that's not very interesting. So the question is how prevalent it is, because I just say like it's Broadcom and Ralink, and you're like, I've never seen a Broadcom or Ralink router. But actually, they sell the chips, but they also sell the design and the software. Basically, sometimes when you buy, I don't know, a D-Link or Linksys or somewhere, they just took the code from Ralink or Broadcom, put it inside an icebox, and they use the software that is given by the manufacturer just to change the graphic, and that's all they do, actually. So since it's almost time, I will go through that. Basically, I'm just saying that most of these guys, they don't care. I tried to contact the manufacturers, they basically don't care. And when sometimes it got some media attention, they were contacted by journalists, they say, hey, someone from the security team will contact you. But usually it was always people from public relations who were contacting. So it shows how much they care about security. It was always like marketing or public relations. So, okay, this guy is same. And another thing is that that's something totally different, but the specification is very clear that the pin that is on the sticker needs to be a random value. It's not something that must be generated from a static value like the MAC address of the thing. Because MAC address is everywhere on the air, so if it's generated from the MAC address, it's very easy to recover the pin. But if you have worked in embedded devices, you know that personalization is very hard. Like having something very different for each device and match the sticker, it's very hard. So if you have something that you already have, like the MAC address, and you just have an algorithm that takes the MAC address and generates the pins for the sticker, and they have the same algorithm in the box, that's so much easy for manufacturing. So, but it's not allowed by the specification. But in practice, they basically also all do that. So even if my attack doesn't work, even if the online brute force doesn't work, most of the time you can find the algorithm on the net to recover the pin code from the MAC address or some other static stuff. most recently was for D-Link by DevTTI S0. He published this algorithm. But on the net, you can find, on Crack Wi-Fi, you can find thousands of other brands that do that. OK. So yeah, that's the article from TTS, DevTTI S0. And well, the conclusion is that if you have WPS enabled on your home router, you should really disable it now, because it's totally insecure. And if you take some time to look at the code of an access point, you will see that you basically don't want to use an access point anymore, because they are really, it's awful. It's really awful. And like, people have just scrapped the surface. Yeah, that's all.
Okay, are there any questions? Yeah. I'll be running.
Faster.
Hi.
Hi.
Have you looked at the security of any of the open source implementations of access points?
Yes, they are pretty good, actually.
So
like, on Linux, I had to go pretty fast, but it's basically they are mostly used host APD on Linux boxes, which calls /dev/random, which is, well, then it's more academic. There is quite a few, well, that's interesting again. There's quite a few academic papers that have been released that say that the Linux random generator is bad. But I've seen nobody in practice who could show me how to break it. I've gone to several cryptographers and say, hey, there's this paper, and this paper that say it's really bad. And they say, yeah, but you know, it's academic. It doesn't work in practice. So in practice, it looks like the Linux stuff is OK.
Yeah, but I'm wondering more about the quality of the implementations of the general access points functionality and stuff like DDWRT and openWRT and stuff.
Yes, so for the WPS stuff, that's what I mean. I looked at the software for WPS on Linux, and WRT is the host APD. I looked at that. I could not find a problem. But I didn't look further than that.
All right. Thank you.
Anyone else? So I have a question. Do you know where the protocol comes from, or did they just kind of make it up?
Yes, I know, because I met some people who told me, but I don't know if I can tell all this stuff, but it's basically, it was Microsoft and Atheros, and I don't remember if it was Siemens or who, and they basically, hey, we need something. And Microsoft say, hey, we have that. Let's try to make it work for that. And you know, it was apparently specification by committee.
Okay. Okay, anyone else? Okay, well then let's have another round of applause.